In the vast expanse of the universe, one constant remains, the ubiquitous presence of light. This brilliant spectacle that brightens our world is so much more than meets the eye. Light, a vital player in the cosmic arena, is our window into the wonders of the universe. Let's start with the basics. What is light? Well, at its core, light is a form of energy, an electromagnetic radiation that is visible to the human eye. It's the reason we can admire a starry sky or a vibrant rainbow. But light is not confined to what we can see. It extends beyond into realms invisible to our eyes, playing a crucial role in everything from radio communication to medical imaging. But why should we care about light when talking about the universe? The answer is simple. Light is our cosmic informant. It carries information from the farthest corners of the universe to our telescopes, helping us unravel the mysteries of distant stars and galaxies. Without light, the universe as we know it would be a void of darkness, its secrets forever hidden from us. Light is more than just a beacon in the dark. It's a cosmic time machine, allowing us to gaze billions of years into the past. When we look at distant galaxies, we're not seeing them as they are today. Instead, we're seeing light that has traveled across the cosmos for billions of years, providing us with a glimpse of the universe's history. Moreover, light holds the key to understanding the fundamental laws of physics. From Einstein's theory of relativity, which was proven by observing how light bends around massive objects, to quantum mechanics, where light behaves both as a particle and a wave. Light has shaped our understanding of how the universe works. In essence, light is a cosmic detective, a time traveler, and a messenger all rolled into one. It paints the universe in vibrant hues and whispers the secrets of the cosmos into our ears. Without light, our understanding of the universe would be shrouded in darkness. As we delve deeper into the nature and properties of light in the coming scenes, remember, every photon has a story to tell. Are you ready to listen? Light, as we know it, is a peculiar entity exhibiting a dual nature. It's like the superhero of the universe, having two identities at once. Imagine a character who is both a particle and a wave, constantly flitting between these two states. This isn't some science fiction concept, but the very nature of light itself. This duality is not just a strange quirk, it's a fundamental aspect of quantum mechanics, the field of physics that explores the world on the smallest scales. Quantum mechanics is the rulebook for how particles like electrons behave, and light is no exception. Think of light as a wave in the ocean, spreading out and interfering with other waves, but at the same time, it's also like a particle, a discrete entity capable of being counted and measured. It's this dual nature that makes light such an intriguing subject to study. This dual nature of light is a cornerstone in our understanding of quantum mechanics. Light, the fastest known entity in the universe, travels at a staggering speed. Racing through the vacuum of space, light darts around at an incredible pace of approximately 186,000 miles per second. That's swift enough to zip around Earth nearly 7.5 times in a single second. Now, why is this speed so important, you ask? Well, it's because of this fixed speed that we're able to understand the universe better. When we look at distant stars and galaxies, we're actually peering into the past. The light from these celestial bodies takes time to reach us. It's akin to a cosmic time machine, offering us glimpses of the universe as it was billions of years ago. Moreover, the constancy of light's speed in a vacuum forms the backbone of Einstein's theory of relativity, fundamentally shaping our understanding of space and time. The speed of light, a universal constant, is a critical factor in our exploration of the cosmos. Light, as we perceive it, is just a small part of a vast spectrum. We're talking about the electromagnetic spectrum, a continuum of all electromagnetic waves arranged according to frequency and wavelength. It's like a cosmic rainbow, with each color representing a different type of wave. At one end, we have radio waves, with their long wavelengths and low frequencies, used in broadcasting and communication. Next up, microwaves, crucial for heating our food and in radar technology. Then we encounter the infrared waves, felt as heat and used in thermal imaging. Here's where we find visible light, the small segment our eyes can detect. Beyond that, ultraviolet light, which gives us sunburns but is also essential for vitamin D production. Further still, X-rays used in healthcare for imaging, and finally gamma rays, with the highest frequency and energy, emitted by radioactive materials and cosmic phenomena. Each wave has its unique properties, interacting differently with matter and space. The electromagnetic spectrum, in all its diversity, is a testament to the multifaceted nature of light. In its particle form, light is made up of tiny packets of energy called photons. These photons are fascinating creatures, zipping around at breakneck speeds. They carry not just light, but also information about the world around us. When a photon interacts with matter, it can be absorbed, reflected, or transmitted. This interaction is what allows us to see and perceive the world in all its color and complexity. One of the most intriguing phenomena is the photoelectric effect. When photons with sufficient energy strike a material, they can knock loose electrons, creating an electric current. This effect, first explained by Einstein, was a key piece of evidence for light's particle nature. It also forms the basis for many of the technologies we use today, from solar panels to digital cameras. Photons, the particles of light, play a crucial role in our interaction with the universe. They act as tiny messengers, carrying information from the furthest reaches of space to our little blue planet. As a wave, light exhibits unique characteristics. It's more than just a stream of particles, it's a series of peaks and valleys oscillating through space. These oscillations, or waves, have a specific pattern and frequency that define the color of the light we see. Now let's delve deeper into some fascinating wave phenomena called interference and diffraction. Interference is the phenomenon where two or more overlapping waves combine to produce a new wave. When the peaks and valleys align, we get constructive interference, resulting in a brighter light. On the other hand, when a peak meets a valley, they cancel each other out, causing destructive interference, which leads to darkness. Diffraction, another wave behavior, occurs when light encounters an obstacle or a gap. It bends around corners and spreads into regions of shadow, creating an array of beautiful patterns. The wave nature of light is a key component of our understanding of the cosmos. Light, a cosmic traveler, journeys through the vastness of space. As it embarks on its voyage, light encounters various conditions and faces numerous challenges. It's fascinating to consider how light, unimpeded by any medium, can travel uninterrupted for billions of light years. This journey is not always a straight line, though. The presence of massive objects like stars and galaxies can curve the pathway of light, a phenomenon known as gravitational lensing. This bending of light is one of the many ways in which the universe reveals its complex and intricate design. Moreover, the propagation of light is affected by the expanding universe. As space itself expands, the wavelengths of light stretch, shifting towards the red end of the spectrum. This redshift is a vital clue for scientists studying the universe's history and its ongoing expansion. The journey of light through space is a testament to the vastness and complexity of the universe. As we've explored, light is a fundamental aspect of our universe. Its dual nature as a particle and a wave, a cornerstone of quantum mechanics, underpins our understanding of many cosmic phenomena. The constant speed of light, unchanging in the vacuum of space, serves as a cosmic yardstick, enabling us to measure the vast distances between celestial bodies. Our journey through the electromagnetic spectrum revealed the diverse types of light, each with unique properties. From the visible light that colors our world to the invisible gamma rays that hint at the most energetic events in the universe, each band of the spectrum offers a different lens through which to view the cosmos. We've delved into the particle nature of light, exploring photons' interactions with matter and their role in phenomena like the photoelectric effect. Simultaneously, the wave nature of light brought us face to face with interference and diffraction, shedding light on the behavior of light in different conditions. Our exploration didn't stop there. We traced the journey of light across the vast expanses of space, understanding the challenges it faces and the conditions that govern its propagation. We discovered how light interacts with matter, leading to absorption, reflection, and transmission, and how these interactions result in the formation of spectra. These spectra opened up a new world of emission and absorption lines, the fingerprints that help us identify elements in distant stars. The concepts of redshift and blueshift introduced us to the dynamic universe where celestial objects are constantly in motion. Light, acting as a cosmic messenger, carries information about these movements, allowing us to decipher the universe's secrets. From gravitational lensing to the formation of cosmic structures, and from the cosmic microwave background to the future of light-based astronomy, we've seen how light plays a pivotal role in our quest to understand the universe. So, the next time you switch on a light or gaze at the stars, remember, light is not just illuminating our world but also unraveling the mysteries of the universe.